At first glance, there's nothing unusual about this place. Rolling farmland, vineyards, and quiet hills stretch across Yeongdong County, a region better known for wine and music festivals than anything geological. It feels stable, ordinary and settled, but beneath that calm surface lies something so vast, so quietly immense, that it completely changes how geologists think about one of the most overlooked materials on Earth. Not gold, not lithium, not rare earth elements, but a mineral so common it's usually ignored entirely. And yet here, it exists in such staggering volume that it has become the largest deposit of its kind ever discovered. Because hidden beneath Yongdong is more than 100 million tons of illite. That number doesn't hit immediately. Illite doesn't carry the same weight in people's minds as precious metals or battery minerals. It doesn't sparkle, it doesn't form veins you can chase through rock, and it doesn't produce nuggets you can pick up and hold. Most of the time it's invisible, locked into fine-grained sedimentary rocks like shale and siltstone, dispersed so thoroughly that it blends into the background of the Earth itself. But scale has a way of changing perception. When something ordinary becomes vast enough, it stops being background geology and starts becoming something else entirely. It becomes significant. Illite is a phyllosilicate mineral, part of the same structural family as mica. At a microscopic level, it's built from stacked sheets of silica and alumina, forming a layered structure that gives it its defining properties: fine-grained, chemically stable and resistant to heat. Unlike other clay minerals such as smectite, it doesn't swell dramatically when exposed to water. Instead, it holds its structure, maintaining stability even in changing environmental conditions. These properties make it incredibly useful, but also incredibly easy to overlook. Because illite doesn't announce itself, it forms quietly, often as the end product of transformation. When feldspar minerals break down, when sediments are buried and altered, when hydrothermal fluids move through rock and begin to change its chemistry, illite can form as a stable, final phase. It's not flashy, it's what's left behind after the system settles. In many ways, it represents the finished state of a geological process. And that's what makes this discovery so strange, because processes that produce illite are incredibly common. They happen in sedimentary basins all over the world. They occur wherever fine-grained sediments accumulate, wherever burial and low-grade metamorphism begin to alter mineral structures. That's why illite is everywhere, but usually only in small, dispersed quantities. A few percent here, a thin layer there, enough to note but rarely enough to dominate. But in Yongdong, something different happened. Instead of remaining dispersed, illite accumulated. It concentrated. Over time, the processes that normally produce small amounts of this mineral seem to have operated at a scale and consistency that allowed it to build into something massive. Not a thin layer, not a scattered presence, but a deposit measured in over 104 million tons. To put that into perspective, most known illite deposits around the world are on the order of a few million tons. 5 million tons would already be considered large. 10 million would be exceptional, but this deposit exceeds 100 million tons, making it not just large but dominant, an outlier on a global scale, and almost no one knew it was there. That's the part that makes this discovery so compelling. This wasn't a remote, inaccessible wilderness. It wasn't hidden deep beneath ice or ocean. It sat beneath a populated, cultivated landscape, farmland, vineyards, communities going about their daily lives. For decades, even centuries, the geology beneath remained largely unremarkable in the eyes of anyone not looking closely enough. Because illite doesn't draw attention. There's no gold rush for clay. Illite sits quietly in the background, useful but unglamorous, important but rarely celebrated. And yet when geologists finally quantified what was beneath Yongdong, the scale of it forced a re-evaluation. Because of that volume, illite stops being a minor industrial mineral and becomes something much bigger. It becomes infrastructure. Industrially, illite is used in a wide range of applications. Its fine particle size and soft texture make it ideal for cosmetics and skincare products, where it can be used as a base or absorbent material. Its chemical stability allows it to be used in pharmaceuticals and agriculture. In drilling operations, it plays an important role in stabilizing boreholes and controlling fluid behavior. It appears in paints, paper and fillers, quietly embedded in products that people use every day without ever realizing it. And increasingly it's being studied for more advanced applications. There's a growing interest in illite's potential role in energy storage systems, particularly in experimental battery technologies. Its layered structure and chemical properties make it a candidate for certain types of solid-state systems, though this research is still in its early stages. It's not replacing lithium, it's not about to revolutionize batteries overnight, but it represents something important, a material that could, under the right conditions, contribute to emerging technologies. And now there's more of it in one place than anywhere else on Earth. That matters, not because it's rare, but because it's reliable. Large, consistent deposits provide stability for supply chains. They reduce dependence on imports. They allow industries to scale without worrying about shortages. In a world where many critical materials are geographically constrained, having a massive domestic source of a versatile material is a strategic advantage. But beyond the industrial applications, there's a deeper geological story here, because deposits like this don't form by accident. Illite formation is tied closely to the movement of fluids and the evolution of sedimentary systems. It often appears in what geologists call argillic alteration zones, where hydrothermal fluids interact with host rocks and begin to change their mineral composition. In these environments, primary minerals like feldspar break down, releasing elements that recombine into clay minerals like illite. These zones can act as markers, indicators of past fluid flow, chemical gradients, and temperature conditions. In some systems, they can even correlate with mineralization processes, appearing alongside or adjacent to ore-forming environments. That's what makes illite more than just clay. It's a record of transformation. In Yongdong, that record has been preserved on an enormous scale. The sediments that eventually became this deposit were likely laid down millions of years ago, in a basin environment where fine particles accumulated slowly over time. As those sediments were buried, compacted, and altered, mineral transformations began to occur. Fluids moved through the system, heat subtly increased, and chemical reactions reshaped the mineralogy of the rock. Clay minerals evolved, smectite transformed, illite stabilized. But instead of remaining a minor component, illite became dominant. Whether due to prolonged fluid flow, consistent chemical conditions, or structural controls that focused alteration, the result was the same: a massive, coherent body of illite-rich material. And that's the scale comparison that changes everything, because when a mineral that is usually background noise becomes the main feature, it forces geologists to ask new questions. What conditions allow this to happen? How consistent were these conditions over time? And where else might similar processes have occurred but gone unnoticed? That last question is the one that lingers, because if something this large can exist beneath a well-known, inhabited region, what else is out there, hidden not by depth or inaccessibility, but by familiarity? How many other ordinary minerals are sitting in extraordinary concentrations, simply waiting for someone to measure them properly? That's the quiet power of this discovery. It doesn't announce a new mineral, it doesn't introduce a new resource category, instead it reframes something we thought we understood. It takes a common, well-known material and shows that under the right conditions, it can become something globally significant. And that's a very different kind of geological story. It's not about rarity, it's about accumulation. It's not about sudden events, it's about slow processes operating over immense spans of time. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.